small but significant local coherence, even in the visually naive animals, and this local coherence increased as a result of training. Now, again, to get at this issue of whether there is information in this initial bias, what we needed to do was to look at the local coherence at the onset of the training and see whether we could predict what would happen to those neurons as a result of training. And what you see here illustrates that we could. So what we looked at was the probability that a cell would change its direction preference. And that's illustrated along this axis. And this is showing you the local coherence before training. And what we found was neurons that had a positive local coherence prior to training were much less likely to change their direction preference than neurons that were sitting in regions where they had a negative coherence, i.e., unlike their neighbors. Now, at this point, you could ask yourself, well, haven't you just said that the map is already there? So there's an initial bias, and experience just builds on it. And you could ask, what role does the visual stimulus actually play in the formation of this map? And so to get at this question, we presented a single stimulus moving in a single direction to see how that would impact the cell's response. If all that was required to build this map was resonant in that initial bias, then basically training with a single direction should be the equivalent to training bidirectionally. And what we found was that it wasn't. So training here, yellow is the train direction. Following training, we found more cells were shifted their response to the train direction. And in fact, if you look at the direction ratio, the ratio of response to the train stimulus versus the opposite stimulus before and after training, you see that many of these cells lie above the line, indicating a shift towards the train direction. If you look at this in terms of a cumulative percentage, you see a shift, again, towards the training direction. So the other question that we had, of course, is the stimulus capable of changing the preference of the cell, even in regions that had an initial bias for the opposite direction? And so here we have local coherence index, where the cells are, the neighbors prefer the training direction. Here's where they prefer the direction opposite. And what you can see is throughout this region, there's a shift in the direction of the training stimulus. So let me sum up what we've said. First, direction columns emerge after eye opening, and they require visual experience for the development. And in this respect, this response property is different than the other properties, orientation, and the initial establishment of ocular dominance. Second, the exposure of visually naive animal to a motion training stimulus induces the rapid emergence of direction columns within hours. The column formation involves an increase in direction selectivity and alteration in single neuron direction preference. There are weak local biases, and we think of them as acting as a symmetry-breaking seed that gets the process of map formation started, but it's clearly not the only bit of information that drives the preference that neurons exhibit. Clearly, the properties of the visual stimulus also exert a powerful influence in determining the direction preferences that neurons acquire. Now, I know I'm running out of time, and I won't spend much time on this, but I just we moved to Jupiter just a little over a year ago, and I wanted at this meeting to be able to present just a little bit of data that came from Max Planck, Florida. And so what I want to tell you about in the last minute or two here is work that we've been doing with the genetically encoded calcium sensor GCAMP, which has tremendous signal to noise. It's letting us do things that we couldn't do with Oregon Green Bapta. And one of the things that it's allowing us to do is to get a much finer temporal picture of the changes that are ongoing as neurons are learning their direction preference. And what you see here are the responses of neurons to two different directions of motion. This is in a visually naive animal. And you can see that most of the neurons are responding to these two directions of motion. And if you add these together, you get a pattern that looks like this, where many of the neurons are only responding relatively weakly. Those that respond, lots of them have a yellow color indicating that they respond almost equally well to opposite directions of motion. Now, with GCamp, what we can do is sample on a much more regular basis and see how these neurons, how the networks and connections between these neurons are building this map. And so this shows you the baseline response. This shows you the changes that we can see in 2 hours, 4.5 hours, 6.5 hours, 10 hours, 15 hours. And we've even gotten to the point now that we can take the animals, put them back, bring them back another day, and go in and look and see what the status of map formation actually looks like. And again, since I don't have much time, I can't tell you what all the dynamics look like, but I can tell you this. It's not simply a process of getting stronger for one direction. You find neurons that start off preferring one direction, shifting to another direction, and going back and forth over this time period. So let me close by just thanking all the people that are responsible for this work. Steve Van Hooser, postdoc in the lab, and Ye Li, a graduate student, were responsible for getting 2-photon in vivo up and running in our lab and doing many of these experiments. Maria Christensen was involved in the single direction training. Rebecca Corlew and Gordon Smith are involved in the new GCamp experiments. And Len White is a colleague from Duke, has been involved in many of these experiments. I need to thank the National Eye Institute, Duke University, and of course my new home, Max Planck Florida Institute. And thank you very much.